10,000 years is not a really long time. Oh, wow, so good to be here. Okay, 60-minute presentation in 30 minutes. This is on consciousness. I don't know if you know what downward causation is. I didn't until like 35 minutes ago. No, it's consciousness, downward causation, formation of matter. You know, we always have to have a scientific title for something esoteric. By the way, I want to publicly thank Brad for making this outstanding wand for me. I'm going to use it as my pointer. So if you cannot see the laser light, well. All right, what is downward causation? I needed a definition too. And I also needed a really neat picture, which I like on this one. It is really through the singularity point into source. It's really drilling down into what is the cause of everything that we see. What is the cause of the effect we see as the physical universe? You know, I've often said here that the universe is the sum of the sentience of all the beings in it. It is the average of all of those realities. Right now we have about 7 billion realities on the earth. And they're all blending together to kind of make an average reality. Well, usually when you have a very large population, the average is pretty stable. Some things get hotter, some things get cooler, some people awaken, some people go to sleep, and it stays pretty stable. That's a statistician's way of looking at things. But the difference between a statistical population and a human population is that we can awaken, we can change, we can become empowered, and we can move the average. So how does this work? What is the visible universe made of? Well, we could say, well, God made the physical universe, and that would be the end of that. Or so my 30 years of religious training would tell me. Or we could say, well, the universe is made of matter. We've drilled it down, we know what it's made of. It's not made of ether. It's not, the earth isn't the center of the universe. Yes, it is. No, it is. Yes, it is. Okay. What is it really made of? Well, we break this down as physicists. Quantum physicists break this into protons, neutrons, and electrons. The first two we're going to talk about last. The last one we're going to talk about first. Well, we thought about this early on. Very, very brilliant people who supposedly broke new ground. Actually, I think we just remembered what we forgot. One very brilliant man, Niels Bohr, came up with a model which we call the Bohr model. It works mathematically very well at looking at matter and how it's built. It looks something like this. We have a nucleus. The positive ones are the protons, the orange ones are the neutrons, and you see the electrons going around in nice and neat in these orbits. Works very well when you're trying to calculate frequencies and atomic weight and all that. But that is not the way atoms really look. That's not the way electrons really work. In fact, I'm a part of my job, I'm an electrical engineer, and one of the crazy questions to ask another electrical engineer is, what's electricity? And they go, what's electricity? Go on, you plug it in, you turn it on, electricity. No. What's the electricity that goes actually through the copper wire? I know we generate it and we use it, we change it into heat and photons of light, but really, what is electricity? Boy, they go, wow, I never really thought about that, what's electricity. Here's another one for you. We have an extension cord that stretches from here to Spokane. I plug it in here. How long does it take for the light bulb to turn on in Spokane? That's a good question. Does it go the speed of light? Does it go faster than the speed of light? Does it wait till the electrons get from here all the way up there on that copper wire before the light will turn on? Interesting question. We don't know the answer. But let's look at electrons. When we cool the universe down, we see that we don't have orbits like Bohr once said. We have what we call Heisenberg uncertainty principles. We have averages. We have probabilities of electrons showing up in certain places. There are two balloon-shaped orbitals we call s orbitals, and the rest of them look like balloons tied together in the center, called p orbitals. These are clouds. These aren't orbits. These are average areas where the electron is supposed to show up. And guess what? It doesn't orbit. It blinks out of existence and blinks back into existence. And there are two questions we still don't know the answer to. One, does the electron actually travel from point to point and we just don't see it? And the second one is that really the same electron as the one that blinked out? Or is that another electron that just kind of comes in like a tag team on every single atom, on every single molecule, in the chairs, in the bodies that make our bodies up, make up our DNA? We are actually exchanging energy for a molecule called ATP in our mitochondria right now. Well, most of us are because you're still awake, but wait till that lunch kicks in. A few of you will dip below the level of consciousness. So electrons are really very, very small points of energy that are negatively charged, that blink into existence around atoms. And we don't really know how to split an electron. We can capture them in an electron capture detector, but we have never learned to split the little beggars. So we just call them electrons, and we can reverse their spins, and we know how they behave, and they make great illumination, great computers, and awesome music. That's what we know about electrons. Now let's move on to the heavyweight. Let's talk about this thing, electricity, this energy that our planet pulsates with, that we see as a potential between the ionosphere of our planet and our planet. What does it look like? I mean, it's really intense. You know, we look at it and it's frightening and it's uncontrollable, and we are very careful when we plug things and turn things on, especially when we open the back panel of things. Some people say, I really don't like electricity, you know. It hurts. I build electric trucks, and one of the things about that DC electricity, when you get up into hundreds of volts, if you touch the two wires, it will shock you. It's quite an awakening. It also makes you younger. That's what I say. The proton, though, is the heavyweight. That's like the difference between this water bottle and James's farm. This is the electron, and James's ranch would be the proton. That's the difference in size. We look at the Earth rotating around the sun, and we could liken it to an electron rotating around a proton. And protons we're learning more about, but unfortunately we're learning about it like somewhat like a 6-year-old would learn how a mechanical robot would work. We smash it on the floor and see what pieces come out of it, and that's how we know the robot's made. Well, I'm not kidding. We're going to smash it right here. The protons, when we slow them down, we are looking for sort of a frozen picture of what this thing's supposed to look like. But when we slow it down, we put it in a detector, this is what it looks like. And this is a motion we call Brownian motion. You get a whole glass full of these things, and you drop a single drop full of ink in the water. Eventually, it will disperse through the water because of this motion. This is the kind of activity that we see on the atomic level. Well, we're interested in this. What makes this go? How does this stay so organized? How is one hydrogen proton like another hydrogen proton, like another hydrogen proton? We don't know. Why does chemistry work the way that it does? We can take reactants of a specific number of protons and neutrons, molecular weight, and mix them together, and we can get reactants reliably every time. Why? What makes up the proton? Well, it's energy. Okay, what's the frequency of the energy? How do I get that energy? What do you form that energy out of? Good question. So, this is the dissection of a proton. We build a little thing called a super collider, and we take hydrogen protons and we pour them into a chamber, and I think my movie started exactly in the middle. I was going to play the whole thing. This is the Hadron, the CERN super collider. We take the hydrogen protons, we pour them into a front end of this, and we strip off all the electrons with a battery. We just reverse the charge and all the electrons come off. So the only thing we're left with now is the proton. And then we electronically accelerate these. We change the charge and we move these things through stage 1 of the collider. We pack them up very tightly and they accelerate on down the tube until they go into what we call stage 1 of the collider. I actually took this 6-minute movie and trimmed it to 3 minutes, but mysteriously, when I closed the lid and opened it back up, the full-length movie, so you're going to get the whole thing. So this gets split into 4 packs, and we accelerate this up to about 90% the speed of light. We do this by adding electrical energy and magnetic energy. These are accelerated around and around and around for about 3 or 4 minutes until this reaches about 90% the speed of light. Now, if you know the equation, E is equal to mc squared, you know the relationship between energy, mass, and the speed of light. As we approach the speed of light, mass gets larger and larger because you can't exceed the speed of light. You could pour more energy in, but mass is just going to increase to meet it because the C in the equation isn't going to change. Notice that we're doing this in resonance fashion. We're hitting those every single time they come around at exactly the right moment until they go faster and faster and faster, and then we spit them out of stage 1 and off to stage 2 they go. This thing is about 200 meters across. That's about from here to the road. So we accelerate them around here and we start pouring more energy into it and we reach about 99% the speed of light. Well, you'll notice that you can't pour more energy into this and make it go faster. You're already about as fast as you can go. So these 1 electron volt electrons increase to about 25 giga electron volts in this stage 2 or stage 3. When they reach this, and they stay in this for about 30 minutes, when they reach this level, they are then slung out of this into a very large collider. Not the collider, another accelerator, which is super cold and has had all the air evaporated out of it, or evacuated out of it with vacuum pumps. And it's deep beneath the earth. And this large one is about 25 kilometers in diameter, and it's underground. It took a lot of money to build this. As we accelerate, we're pouring more energy, more electrical energy, and more magnetic energy into this, and you'll see it just becomes one blur of light. Now these are just packs of hydrogen protons. More and more hydrogen is added to it until there's about 2,080 packets of hydrogen protons in this. And then they're spit out into this one. This one will accelerate these protons up to, well, they'll stay near the speed of light, but we pour more energy into them until they're 25 giga electron volts. And then, as it reaches maximum speed, it's close to 5 tera electron volts. And then they're crossed like a mean game of figure 8. Half the pack sent one way, half the pack sent the other way, and then they sit back and watch for the fireworks. Sooner or later, you know what's going to happen, don't you? Sooner or later, the protons are going to collide at this X. And when they do, it's like very expensive, very educated 6-year-olds slamming a mechanical robot apart on the street to see what makes it work. And sure enough, at the right moment, the right time, they might have to wait a half an hour for this to happen, but eventually, the particles are going to collide. When they do, they have detectors waiting there to catch the action. These detectors are digital. They're tuned to literally fractions of wavelengths, and they're just waiting for the right frequency to come out of there so they can identify it. And when this collision happens, all of that energy happens and is over in a few femtoseconds. Femtosecond. You know what that is? 10 to the minus 15 seconds. That's really short. That's like faster than that. Okay, faster than that. No, it's really, it's right now. All of these species are collected, and now we very wisely, very maturely, as the advanced human race that we are, say, Now we know what protons are made of. They're made of these. They're made of these subatomic particles. And each one of these is, let's see, what do they say, about 10 tera electron volts when two of them collide head on. That is collected by a supercomputer, it's analyzed, and guess what we found? Frequencies! No more particles, just energy. Darn. We wanted to get, like, you know, pieces of the robot. We didn't want it to completely fly apart into different colors. So as we realize this, we kind of come to the conclusion that if we go to downward causation, what causes this, causes that, causes this, causes that, we get all the way back to the beginning, which is energy. And what happens when you get to the ultimate causation? What happens when you arrive back at that energy point in your search? Well, it's interesting, because the human consciousness can do this. We can imagine this in our minds. That's why we build things like a collider. That's why we build spacecraft to go to other planets. Even though we can imagine the universe, even though we can see galaxies, we can see solar systems, we can see this subatomic formation, we want to experience it. So we're building equipment and building instruments so that we can experience it in the third person. But in reality, the average 5-year-old knows how this is done. They'll forget it by the time they're 13. Then they'll remember it when they're 52. We get to the point of consciousness. And then somebody asked me the other day, what's consciousness? Yeah, right. Okay, what's electricity? We don't really know, except that everything has it. Rocks, stars, plants, dogs, people, fish, Democrats. Okay, I went a little too far. The point is that we have this common link throughout the universe. All sentient beings do, whether they're human or whether they're not human, if they're sentient. Now, Bob made some remarkable comments that I felt familiar with, and that is that we've lived many lifetimes, and most of us in this room feel like we've lived lifetimes on other worlds. And with either regression or remembrance or dreams or somehow knowing how to do this, we say, where did I learn how to do that? Well, I remembered it somehow. I don't really know how. But I have a skill with that. I have a memory with that. I have a smell that I remember. I have a movement that I remember. I have a balance that I remember. I remember music or mathematics or art or medicine. These things I remember. Is this part of one big consciousness in the universe? Or is it a piece of each one of us as we have accumulated experience on, shall I say, a subconscious level over eons and eons of lifetimes? And the answer is yes to both questions. So when we drill into this tiny little hole of the proton and we come out the other side, perhaps it's the universe within. Perhaps it's a whole nother set of galaxies, a whole nother set of stars. And we can go back and forth from universe to universe. It is a physics fact that we lose energy from our universe to other universes through black holes or something like unto it. It must also be a physics fact that information comes into our universe from other universes. A transfer of energy is a transfer of information. That we know. Even the Tibetans knew it. And as they put their music and their thought and their mathematics and their mandalas together, it was as clear to them as it is now becoming to our physics community. The main thing to remember here, not to get lost in the minutiae or get worried about forming a dozen black holes outside of Venice or outside of France. Vienna, that's what I wanted to say. I was thinking pizza. I don't know how to is not to get worried about it, because at the end of the day, you are source. You come from source. You will return to source and come back out of source many times until you're tired of it. Then I guess you can go back and go to sleep. Somebody asked me one time, well, what's it like to go to heaven? I said, well, actually, this is heaven. Oh, they were really disappointed. This cannot be heaven. I said, no, really, it is. You could bring it right here. Two people right next to each other. One is in heaven, the other, well, somewhere else. I would think that the opposite of heaven would be knowing everything. No mystery. Nothing over the hill. No greener grass. No frontier. Nothing to learn. That would be the opposite of heaven. That's why I think Earth is cool. And if you want to participate with me some night, we're live Sunday nights on X Squared Radio, 5 to 8 p.m. Pacific. Thank you so much. That's 30 minutes. All right, I guess we're going to have a panel now, right? All right, what are we going to do? Take a 7 3/4 minutes break.
Get it set up.
That's it. And then we're going to get it set up.